Hello my dear students, this is the first video of the series about analytical geometry. In this video I am going to give you an introduction about coordinate systems. But before we begin, I suggest you to subscribe this channel and press the notification bell to receive updates about related videos. We should start by the definition of coordinate system, which states that it is the system that uses one or more numbers to uniquely determine the position of the point on the manifold. The numbers used to determine the position of point are called coordinates, and they mostly take values as real or complex numbers. The simplest form of coordinate system is to locate the point on the real line, which is the one-dimensional coordinate system. In this system, an arbitrary point marked by capital letter O called origin is chosen on the given line such that the numbers on the right-hand side of the origin are taken as positive and all the negative numbers are marked on the left-hand side of the origin. Each coordinate on the given line corresponds to a unique point, and each unique point corresponds to a unique coordinate. For example, the position of the point 0.7 is between 0 and 1. Similarly, we can determine the position of any point on the given line. Then we have two-dimensional coordinate system. In this system, two mutually perpendicular lines are chosen crossing each other at a point called origin, and it is denoted by capital letter O. This results in four quadrants. Let's mark them with first, second, third, and fourth quadrant. The horizontal line is called x-axis and vertical line is called y-axis. Two-dimensional coordinate system is called plane. There are two types of systems to locate the position of the point in two-dimensional coordinate system. Those are Cartesian coordinate system and polar coordinate system. Let's first look at the Cartesian coordinate system. A point P1 in the two-dimensional Cartesian coordinate system is uniquely determined by an order pair x, y, where the value of x, which is called the x-coordinate, is the distance of a point from y-axis, and the value of y, which is called y-coordinate, is the distance of a point from x-axis. In other words, to reach out the point P1 from origin, we have to move x units distance along x-axis and then y units distance along y-axis direction. Similarly, moving y units along y-axis and then moving x units along x-axis, we can reach to the point P1. The position of the point in the plane depends on the value of x and y. The point lies in the first quadrant if the value of x and y are positive. The point lies in the second quadrant if the value of x is negative and y is positive. The point lies in the third quadrant if the values of both x and y are negative. And the point lies in the fourth quadrant if the value of x is positive and y is negative. Moreover, for y is equals to 0, the point lies on the x-axis on the right-hand side of origin if the value of x is positive, and on the left-hand side of origin if the value of x is negative. Similarly, for value of x is equals to 0, the point lies on y-axis above the origin if the value of y is positive, and it is below origin if the value of y is negative. If both the values of x and y are 0, then the point lies at the origin. In contrast to the Cartesian coordinate system, where we use distances from x and y axis to determine the position of the point, we can also determine the position of a point by the numbers rho and theta, where rho is the length of the position vector of a point and theta is the angle made by this position vector with positive x-axis. This is called polar coordinate system. Now let's look at the relationship between Cartesian and polar coordinates. For example, x and y are the Cartesian coordinates of the point P. Let us represent the length of the position vector of a given point by r, and theta is the angle it makes with positive x-axis. Then by applying distance formula between O and P, we have r is equals to square root of x square plus y square, and from right angle triangle OAP we have sin theta is equals to y upon r and cos theta is equals to x upon r. Dividing sin theta by cos theta, we get tan theta is equals to y upon x, and to get the value of theta we can take the inverse of tangent on both sides. We get theta is equals to tangent inverse of y upon x. Hence, given the Cartesian coordinates x and y, we can get polar coordinates by the formula r is equals to square root of x square plus y square, and theta is equals to tangent inverse of y upon x. Conversely, given the polar coordinates r and theta, we can obtain Cartesian coordinates by the formulas x is equals to r cos theta and y is equals to r sin theta. Then we have three-dimensional coordinate system. In this system, three mutual straight lines are chosen, crossing each other at a point called origin. This results in three planes. Let us mark them as xy plane, yz plane, and xz plane. Three-dimensional coordinate system is called space. There are three types of systems to determine the position of the point in three-dimensional coordinate system. Those are Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Let's first look at three-dimensional Cartesian coordinate system. The position of the point P in this system is determined by the ordered tuple x, y, z, where x, y, and z are the distances along x, y, and z axis directions respectively. To locate the point P in this three-dimensional Cartesian coordinate system, starting from the origin, we have to move x units along x-axis, then y units along y-axis, and then z units along z-axis direction. The point is on the xy plane if the value of z is equals to 0. Similarly, the point lies on yz plane if the value of x is equals to 0, and the point lies on xz plane if the value of y is equals to 0. The point lies on x-axis if the value of y and z is 0. The point lies on y-axis if the value of x and z is 0, and the point lies on z-axis if the value of x and y is 0. And if the value of x, y, and z is 0, then the point lies at the origin. In contrast to three-dimensional Cartesian coordinate system, the position of the point can also be determined by the numbers r, theta, and z, where r and theta are the polar coordinates of the projection vector of the position vector of a point. Now let's look at the relationship between Cartesian and cylindrical coordinates in three-dimensional coordinate system. For example, x, y, and z are the Cartesian coordinates of the point P. Let us represent the position vector of a point P by the vector OP. Then the projection of the position vector OP on xy plane is denoted by the vector OB, which makes an angle theta with positive x-axis. The polar coordinate r is the length of the vector OB, hence r is equals to square root of x square plus y square, which can be obtained by simply applying the distance formula between O and point B. From the right angle triangle OAB with right angle at the point A, we have x is equals to r cos theta and y is equals to r sin theta. To get theta, we divide y by x and we get theta is equals to tangent inverse of y upon x. Finally, the third component of the cylindrical coordinate is same as Cartesian coordinates. Hence, given the Cartesian coordinates x, y, and z, we can get corresponding cylindrical coordinates by the formulas r is equals to square root of x square plus y square, theta is equals to tangent inverse of y upon x, and z is same as the third component of Cartesian coordinates. Conversely, given the cylindrical coordinates r, theta, and z, we can get corresponding Cartesian coordinates by the formula x is equals to r cos theta, y is equals to r sin theta, and z is same as the third component of the cylindrical coordinates. Apart from Cartesian and cylindrical coordinate system, we have a spherical coordinate system. In this system, the position of the point P is determined by the order tuple rho, theta, and phi, where rho is the length of the position vector of the point P, theta is the angle made by the projection vector of the point P on xy plane, and phi is the angle made by the position vector of the point P with z-axis. Now let's have a look at the relationship between spherical and Cartesian coordinates. Let P be the given point with the Cartesian coordinates x, y, and z. Let the length of the position vector OP is denoted by rho, which makes an angle phi with z-axis. Then rho can be computed as square root of x square plus y square plus z square. The projection vector of position vector OP on xy plane is denoted by OB, which makes an angle of theta with x-axis. Let us represent the length of the projection vector OB by r. Then from the right triangle OAB with right angle at point A, we have x is equals to r cos theta and y is equals to r sin theta. From the diagram, we can clearly notice that the vectors OB and CP are concurrent. Hence, from the right triangle OCP, we have sin phi is equals to the length of the vector CP divided by rho, which can also be written as r upon a rho. Hence, to get the value of r, we can cross multiply and get r is equals to rho sin phi. Substituting the value of r back into the value of x and y, we can get x is equals to rho sin phi cos theta and y is equals to rho sin phi sin theta. To get theta, we divide y by x, and finally we get theta is equals to tangent inverse of y upon x. Moreover, from right angle triangle OCP, we have z is equals to rho cos phi, or we can write down the value of phi as cosine inverse of z upon rho. Hence, given the Cartesian coordinates x, y, and z, we can obtain their corresponding spherical coordinates by the formula rho is equals to square root of x square plus y square plus z square, theta is equals to tangent inverse of y upon x, and phi is equals to cosine inverse of z upon rho. Conversely, given the spherical coordinates rho, theta, and phi, we can obtain their corresponding Cartesian coordinates by the formula x is equals to rho sin phi cos theta, y is equals to rho sin phi sin theta, and z is equals to rho cos phi. Note that in order to convert the cylindrical coordinates to the spherical coordinates or vice versa, we need to first convert them into Cartesian coordinates.